Alright, so our next problem reads, an open container initially at 1 atmosphere and 298 Kelvin contains 1 kilogram of liquid water. The container is sealed without removing the air, then heated to a pressure of 2 bar, at which point the vapor space contains 0.3 moles of water. What is the final temperature and what is the total volume of the container? So, first thing we're going to want to do is draw a diagram of this situation and then write out what we know and what we're looking for. So, first we want a diagram, so we're going to have some sort of container. So that can represent our container, and it says it is filled with water, partially with water, and it is originally open to the atmosphere. So that means there's going to be air inside this container, and then there's also going to be a little bit of water vapor from the liquid water. Because water and water vapor are going to be in equilibrium with each other at the beginning of this problem. So what do we know about this initial situation? So we can write that beneath here. So we know that the pressure is initially 1 atmosphere. So we know the initial pressure. Right now I'm not going to worry about the specific values that go along with these. We're just going to be working in variable form. So we know the initial pressure, and we also know that the initial temperature is 298 Kelvin. So we know the initial temperature. And then it says the container contains 1 kilogram of water. So we also know the mass of the water. Alright, so then container is closed up. So we've got air trapped inside, water vapor and water, and then the entire system is heated up until it reaches a pressure of 2 bar. So we know what the final pressure should be. We're going to write this one as pressure final desired because of the way that we're going to be solving this problem. So we're going to have a Python script that is going to calculate the pressure final based on a value that we input, and then it's going to decide is that value that we randomly inputted, is that too high or too low, and it's going to adjust it incrementally, and then it'll iterate through these calculations until the pressure that it calculates is equal to the pressure that we specify as desired. So we're going to call this the desired final pressure. And that's going to be similar to the desired moles of water vapor. So, same thing with the moles of water vapor. Those are desired. Alright, so this is what we know about our situation. Now let's find out what we're looking for. What variables are we trying to solve for? These are the variables that we need. So it asks what the final temperature is. So that's the first variable we're going to need to find. Temperature final. And it asks what's the total volume of our container. So the total volume of the container. Alright, so now that we have our problem set up, let's think about some equations that we can use to end up finding these values over here. So, one thing you'll notice is that we are given the initial temperature. And if you'll remember from one of the previous videos that I have done, we can find, or the Antoine equation is the log base 10 of the pressure is equal to A minus B over C plus D. So that means that we can input a temperature and get out a pressure based on some experimentally determined constants. I mean, it will output the log of the pressure, but then we can take, we can reverse that log and get the actual pressure. That means that we are able to find the pressure of the water in the initial situation. And we're going to end up needing the temperature final, so we'll be able to use this equation to solve the temperature final for the pressure of the water final as well. So that means, so let's just write that out. So the pressure of the water initially, we're going to be able to find using this the initial temperature. So that's going to be found using the Antoine equation. And then we can also set out an equation for the pressure of the water finally to also be part of the Antoine equation. So that's how we'll get those two values. Now, the next thing we're going to do as we're looking at this problem is we need to know how much stuff we have in here. So we're given the mass of the water. We're given what we want the final mass of the water vapor, moles of the water vapor molecules are. But we really don't know anything about how much air is in this container. So let's find an equation to find that out. So one thing we're going to do for this problem is we're going to assume ideality of the two gaseous phases. So that means that the equation PV equals nRT is going to apply to this situation. And it also means that molecules of water vapor aren't going to see each other, and they're not going to see or interact with molecules of air, which means we can kind of treat them separately, and it'll make some of our calculations easier. So let's work on finding out how much air. So PV equals nRT can give us the moles. So let's find moles of air. So the moles of air will be equal. The moles of air initially, the moles of air are going to remain the same throughout the entire problem, so we don't need the initial there. So it's just the moles of air are going to be equal to the pressure of air initially times the volume of the air initially over the gas constant times the initial temperature. Alright, so looking at this, we can find the gas constant. That's easy, that's a constant. Temperature initial we're given, so that's all good. We don't know about the pressure or the volume yet. So let's look at the pressure first. So one thing we are given is we're given the total initial pressure. So then we need to find the partial pressure of the air initially. So that's pretty straightforward. I'm going to draw my arrows in a different color so it's more clear. So we're going to take that up there. You can't really see that color. Let me try a different one. Okay, that one's better. So we're going to take, the partial pressure of the air is going to be equal to the total initial pressure minus the partial pressure of the water initially. So you'll notice we can have the values to solve this. Got the initial total pressure, and we've already decided how we can find out the partial pressure of the water. So we're all good there. So next thing we're going to look at is this volume. So remember how I said we're going to assume ideality of these phases. That means that the volume of air initially and the volume of the water vapor initially are going to be equivalent because the molecules do not interact with each other, and therefore they're going to take up the same volume. So we can simplify this a little bit. Instead of specifying just that that's the volume of air, that's just the volume of anything that's in the vapor phase. So then we'll come over here and we'll say the initial volume of anything in the vapor phase is going to be equal to the total volume. So there we go, that's something that we're looking for. The total volume minus the volume of the water initially. Because the volume total won't change, but the volume of the water might, because some might evaporate, or some of the water vapor in the air might condensate, those sorts of things. So we'll specify initial here, but that one, the volume total is not going to change. So we don't know this, or we're using this equation to find this one. This is something we're looking for, so we really need another expression for the volume of the water initially. Well, you'll notice that we have the mass of the water initially, and density is something that relates both volume and mass. Density is something that can pretty easily be found for common substances like water. So we're going to write it down the general equation that density is equal to mass over volume. So we can use that here. That means that the volume of the water initially is going to be equal to the mass of the water divided by the initial density of the water. So I put the initial here because density is dependent upon temperature, and since the temperature is changing, the density will also change. Alright, so next, let's look for the mass of the water liquid. So we have the total mass of the water liquid, which means we can find the mass of the water liquid. So the mass, oh, that's the wrong color, sorry. Mass water liquid is equal to the mass of the water total, so that's that, minus the mass of the water vapor, right? Okay, so we know this. We're going to need the mass of the water vapor. So we don't know the mass of the water vapor, but we do know how many moles of water vapor we want. So mass and moles are related via the molar weight of the substance. So the mass of the water vapor is going to be equal to the moles of the water vapor that we desire times the molar weight. Right? Alright. What else can we find? Alright, so we know the volume of the vapor initially. We found an equation for that. But how will we find a volume for this vapor phase in the end? So it's going to be very similar to this row right here. We're going to have the volume of the vapor final is going to be equal to the total volume, which is again something that we're looking for, minus the volume of the water finally. And similar to up here, we can find the volume of the vapor finally, or the volume of the water finally, using the density. So the volume of the water final is going to be equal to the mass of the water, which we're given, over the density, and this will be the final density since we're working with the final volume as well. Alright, so the last thing we're going to need to find is we're going to want to write an expression for each of these variables down here, since we're going to have Python run the code, find the variables, and then compare them to our desired values, as opposed to just plugging these in. So we're going to need equations for both of these, so we'll start with the final pressure. So the final pressure is going to be equal to the pressure of the air finally plus the pressure of the water finally. These are partial pressures of the air and partial pressure of the water. Well, we've already found the partial pressure of the water, and we use the Antoine equation for that. And then, so we just need to look at this final pressure of the air. So for that, we're going to use PV equals nRT. So we'll have the final pressure of the air is going to be equal to the moles of air, which we've already found an equation for, times the gas constant, times the final temperature, which is something we're looking for, over the volume of the vapor finally, which is, again, something we've already come an equation for. So then the only thing that's left is the moles of the water vapor. So this, again, we can use PV equals nRT, so we'll have moles of the water vapor final is going to be equal to the pressure of the water vapor, or the pressure of the water final. That's the partial pressure of water times the volume of the vapor final, which again we've already have an equation for, over the gas constant times the final temperature, which is what we're solving for. And there we have all of the equations that we're going to need to solve this problem. Right, so the next thing I'm going to show you how to do is how to use Python code to solve this problem. So first thing we're going to need is we're going to need to import this library that's on GitHub. And what this library is going to do is it's going to solve an equation that's very similar to the Anton equation, but it's slightly more complex and slightly more accurate. So basically we can input the temperature and it will output the pressure for specific compounds. And then it will also tell us the density of those compounds. So to get this, we're going to go to code up here, and we're going to copy this link. We're going to go over to our Python, and we're going to use the git clone command with that link. And then we're going to want to import sys, and then we're going to use sys.path.insert, and we're going to insert the file path. Alright, so that is all just importing this library from GitHub as something that we can use. And it's giving me an error, but that's only because I have already loaded it in prior to making this video. So it'll still work just fine, it's just telling me that I've already done it. So we've made this something that we can import, but we haven't actually imported it yet. So the next thing we're going to do is actually import it. So this is very similar to how we've imported like NumPy and stuff like that before. So we're just going to import CHE tools as CHA. So we'll just call it CHE to make it easier to type. And then we're going to want to specify what compounds we're looking at. So we'll assign these to a variable. So P equals, we'll call this variable P, and we'll do CHE.props. So this is finding the properties. And then we give it a vector with all the compounds we're going to be using. So for this problem, that's just water. All right. And then I think this is supposed to be tools.che. So, yep, I just typed that backwards. Sorry about that. So the other thing that we're going to want to import this is from SciPy optimize, and we're going to want to import the root function. So this is what's going to solve our complex system of equations for us. Alright, so now we're ready to start working on this problem. So we can enter the things that we know. So over here I have our problem written up here, and then I have the equations that we derived just for reference. So what do we know? We know the initial pressure, and that is 1 atmosphere. So come over here, so we can specify that the initial pressure is equal to 1 atmosphere, but we're probably not going to want our pressures in atmospheres, we're going to want them in pascals. So 1 atmosphere is equal to 101.325 pascals, so we'll just type that in here, 101.325. Alright, so next, we're given the initial temperature as 298 Kelvin, so we can enter that. Temperature initial is equal to 298 Kelvin. Alright, so the next thing we're given is that the amount of water, the mass of water, is 1 kilogram. So the mass the water is equal to 1 kilogram. Alright, so then next things we're going to need are the final pressure that's desired and the final amount of moles that's desired. So the final pressure we desire is 2 bar. So pressure final desired is equal to, so 2 bar, again they don't give us the pressures in atmosphere, so we're going to have to convert it. So 1 bar is 100,000 pascals, so 2 bars is 200,000. So that's 200,000 pascals. And then we're going to want the moles of water vapor desired. And that is going to be equal to 0.3. And then the other constant we have is going to be R, used in the gas, the ideal gas law. So R is equal to 3. I forget. Hold up. Gas constant 8.314. That's what it is. 8.314. Alright, so now we're ready to start defining our equations. So we're going to define them as a function, but then we're going to use this root function to optimize. So define our equations, we'll just call that EQS, and we're going to have to import something, or input something. So we'll input a vector called v. Alright, so now we need to decide what this vector v is going to be. So the vector v is going to be our guesses for these variables that we're looking for. So we're going to guess for the temperature final and the volume total. So we can unpack that by doing the temperature final and the volume total are equal to v. So that unpacks that. So now let's start looking at our equations. So we're going to have to go like kind of right to left on these. For the most part, it's still top to bottom. So that, P air initial is defined before it's used in the equations over here. So we're kind of going to go the reverse of all of the errors. We could start up here with using an Antone equation like equation. So, and that will be from this CHD tools that we used earlier, or that we imported earlier. So the pressure of water initial is going to be equal to P dot Pvap, so that's the partial pressure of the vapor, and we need to define a temperature, so we're going to use the temperature initial. So that's going to be our initial pressure for the water vapor. And we can do the same thing for the final, so the pressure of the water final is going to be equal to P dot Pvap for the temperature final. Alright, so what do we have next? Next equation we have, so we're going to start left to right again, so let's start with this one up here. So the pressure of the air initial is equal to the total pressure initial minus the pressure of the water initial. So the pressure of the air initial is equal to the pressure initial minus pressure of water initial. Alright, so we've already defined pressure of water initial up here, so Python won't have any problem plugging the value it gets up here into the value from down here. Alright, and then this pressure initial we defined all the way up here. Right. So the next thing we have is then we're going to need to do these ones before we get to this moles of air over here. So the volume of water initial is equal to the mass of water over the density. So volume of water initial is going to be equal to the mass of water divided by, so the density, we're going to again use this library I imported earlier, so it's going to be P dot rho L, so the density of the liquid, and this is going to be at our initial temperature. So that will just give us the density at the initial temperature. Right? Right, so the next we're going to have volume of the vapor initial is equal to the total volume minus the volume of the water initial. So volume of vapor initial is equal to the volume total minus the volume of water initial. Right? And then, so next we can find the moles of air. So the moles of air are going to be equal to PV over RT. So moles of air are going to be equal to the pressure of the air initial, with the parentheses, the pressure of the air initial times the volume of the vapor initial divided by R times the initial temperature. Right? And then, so our next set of equations, we've got the mass of water vapor is equal to the moles of water vapor that we desire times the molar weight. So we've got the mass of water vapor is equal to the moles of water vapor that we desire times, so the molar weight of water, that's going to be 18 times 10 to the negative third kilograms per mole. Right? And then, so then we have the mass of the liquid water is equal to the total mass of the water minus the mass of the water vapor. So the mass of the liquid water is going to be equal to the mass of the water minus the mass of the water vapor. Right? So next row, we've got the volume of the water final is going to be equal to the mass of the water divided by the density of the water in the end. So volume of water final is going to be equal to mass of water divided by, again we're going to use this library from earlier, so P dot rho L, but this time use the final temperature. Alright, and then from there we're going to find that the volume of the vapor final is equal to the total volume minus the volume of the water final. So volume of vapor final is equal to the volume total minus the volume of the water final. Alright. And then next we have the pressure of the air final is going to be equal to nRT over V. So the pressure of the air final is going to be equal to the moles of air, we'll put parentheses in moles of air, times R times the final temperature divided by the volume of the vapor final. And then the next equation we have is the final pressure is equal to the pressure of the air plus the pressure of the water final. So final pressure is equal to the pressure of the air final plus pressure of the water final. And for our last equation, we've got the moles of the water final, or the water vapor final, is equal to PV over RT. So the moles of the water vapor final is equal to the pressure of the water, more parentheses, pressure of the water final, I forget, times volume of the vapor final over RT. So times the volume of the vapor final divided by R times the final temperature. Alright, so these are all the equations that we need, but we need our function to return something. So we're going to want, remember how I said earlier, we're going to want our equations to like kind of run through themselves with an initial guess, and then it's going to iteratively change the guess until the pressure final is equal to the pressure final that we desire, and the moles final of the water vapor final are going to be equal to the moles that we desire. So one way to do this is to have, the pressure final minus the pressure final that we desire. When that equals 0, then it has found the solution. And that's what the root equation, or the root function that we imported is going to do. So we need this to return a vector with two values. The first of which is going to be the pressure final minus the pressure final desired. And the second will be the moles of water vapor final minus the moles of water vapor desired. Alright, and shift enter. So now we've got all of our equations in there. So now let's use the root function to find our solution. So we're going to use root, and so we're going to take the root of our function equations, and we're going to want to import guess. So let's say we guess the final temperature is going to be about 350 Kelvin, and that our initial volume will be about 0.1. Right, so let's shift enter and see what happens. Alright, so it's given us an answer. It's given us a lot of stuff. We really only need this last line here, which is an array with two values in it, and these two values are the final temperature and the total volume right there. So to get just those values, we put dot x. Alright, so now you see we just have these two, and then we can unpack them into separate variables if we want. So, temperature final, volume total is equal to that. And then if we display the final temperature, we see that it's about 366 Kelvin. And if we display the volume total, we see that it's about 0.0126. And that is how you solve this problem using the Antoine equation. Or not the Antoine equation. This is how you solve this problem using Python.